No, it was just a big wall of dust, and there were storms in Tucson that started this gigantic outflow boundary, something like 100 kilometers wide. Closed the airport for an hour, and the dust was very dense. That's right, this is our monsoon. It's a pleasure to be with you again, and thank you for this opportunity to speak to you today. My subject this morning is on something that we call the local ensemble transform Kalman filter, which is an approach to Kalman filtering for complex spatiotemporal models that relies on some of the chaotic dynamical characteristics, in particular of weather models, but also of other types of fluid flow models. And so it uses some of these ideas of local low dimensionality in a way that makes the computation tractable. So that's the subject for this morning. Again, I'd like to thank many coworkers who have been, it's been a privilege to work with, Istvan Sunyog, Brian Hunt, Edward Ott, Eugenia Kalman, Jim York, and many others who have actually extended this work to other types of models. So once again, a preprint repository is available here at the weatherchaos.umd.edu website, and then on my home page are some MATLAB exercises and a picture of my dog if you ever want one for posterity. Okay, so the main thing, the main topics this morning, I will be talking a little bit about the theory, and much of what I have to say here concerning the theory is in this paper with Brian Hunt and Istvan Sunyog that appeared in Physica D. Essentially what this paper does is it presents a refinement of an initial implementation of a filter that was described in this 2004 paper in TELUS. The 2005 paper reported some numerical results with what are called perfect model experiments. That is, essentially we were assimilating synthetic data from a global weather model to test in principle the performance of this filter and how it degrades with increasing sparsity of data. This last paper in TELUS A in 2008 presents results with real data. So here model error becomes important. So what I thought I would do this morning is talk primarily about some of the mathematics behind this, and then just summarize very briefly some of the real data. Again, if there are things that are not clear, please let me know, and I would be happy to stop and answer questions. So to summarize some of the main points from yesterday's lecture, we are talking about, in the case of a numerical weather model, a chaotic process. And a chaotic process is one where every point is sensitive. That is to say that if there is an error in your knowledge or measurement of the initial condition, then eventually that error becomes very large, and so we call this notion sensitive dependence on initial condition, or simply that every point is sensitive. And so these uncertainties in initial conditions, at least for a little while, tend to grow exponentially. Now, Ed Lorenz had a back of the envelope calculation in which he estimated that approximately the uncertainty in, if you will, the global weather state vector for a typical model would roughly double every 2 days. And so what that means is, as a practical matter, the 2 weeks would be pretty much about the upper limit for forecasting the weather with any great detail, given the likely uncertainties in one's ability to estimate the current state of the atmosphere. And so, because these uncertainties in weather models tend to grow rather quickly, the initial conditions for the model have to be updated rather frequently in order for the weather models to track reality. And so, in current operational practice, that happens 4 times a day, every 6 hours. Now, the other idea that we introduced yesterday was this notion of an ensemble dimension. Remember, we are using ensembles of forecasts as a Monte Carlo procedure to try to estimate the uncertainty associated with a given set of initial conditions. So we treat the initial condition as a random vector, and we think of it as having some probability density function associated with it. That PDF is very complicated. We may not know all of its details, but we will try to sample from it in a way that we hope is representative of the typical errors or uncertainty. So when one thinks of an ensemble then of forecasts, we are actually forming a matrix. The matrix has as many columns, let's say, as there are components in the forecast vector, and there are as many columns as we care to generate ensembles. So if we had, let's say, a local case, maybe over a typical synoptic region, n might be on the order of several thousand. That would be the size of the state vector over, let's say, France or similar sized region. And then k would be the number of forecasts that we are integrating at any given time. So that matrix would have a singular value decomposition associated with it. The singular values are S1 through Sk, and so we define this notion of ensemble dimension as the ratio of the squared sum of the singular values divided by the sum of squares of the singular values. The idea here is that the denominator is essentially the total variance, if you will, about the mean of the ensemble vector. So it's, if you will, it's sort of a rough measure of the eccentricity of some ellipse. And so just to recall this idea from yesterday's lecture, if we do this in two dimensions, if we imagine a forecast model with 2 state vectors, x and, or 2 components, x and y, but we run, let's say, 100 forecasts, then if in this particular distribution of points, we actually have associated then a matrix whose singular values are both approximately equal, and so the E dimension here is roughly 2. The idea is that these points are more or less filling up a 2-dimensional subspace. Here we've taken the same points and multiplied them by some particular matrix, and now in this case the spread here is roughly 4 times larger in one direction as in another, and so the E dimension here is about 1.4. It just reflects the idea here that things are becoming a little bit more one-dimensional than they were in the previous slide. And here's a more extreme case where S1 is approximately 20 times as large as S2, and in this case the ensemble dimension is about 1.1. Things here are very close to being one-dimensional. So this generalizes the notion of the dimension of a subspace. The dimension of a subspace is always an integer, 1, 2, 3, 4, and so on. Here what we're doing is we're saying, well, it's kind of between 1 and 2 in some way that is descriptive of the scatter of the points. Now, we use this notion in a higher dimensional context with, let's say, a forecast model that might have several thousand variables in a typical region of interest. But what we mean by local low dimensionality is that these ensembles, if I were to take an ensemble of 100 or 200 solutions and I look at what is their spread over, let's say, a typical synoptic region, then I can think of those vectors as forming a matrix that is 3000 by k, and then this will have, of course, k singular values that are non-zero. So what DJ Patil and others did, so this was pretty much the topic of DJ's thesis, and this was reported in Physical Review Letters back in 2001. This experiment was done with ensembles on the order of 100 to 200 vectors, and what they found is that for, in particular, the global forecast system, which is the U.S. Weather Service model, they were to run this model with a resolution of roughly 150 to 200 kilometers, T62 for those of you who know what that means. They found that the ensemble dimension tended to be roughly about 40. So if these vectors were really, let's say, random, then the ensemble dimension would basically be as large as k. If I took 200 ensembles, then it would sort of fill, if you will, a 200-dimensional subspace of a 3,000-dimensional state space. But in fact, that's not what happens. The empirical finding is that these vectors tend to span a much lower dimensional subspace than that. And so in this respect, we think of a global weather model as having, if you will, a local attractor whose unstable manifold is something more like 40 dimensions. And so the idea that we want to exploit when we do Kalman filtering is we want to try to reduce the computational complexity of the objects that we look at. And this number 40 tends to be rather important, and it comes up in a way that I will explain. Now, yesterday we talked a little bit about the analysis of fixed points, but here what I'd like to think about is a more general context. In the center here, think of some true atmospheric state vector, which you don't know, and think of the blue circle as a PDF maybe that represents perhaps our measurement uncertainty in in our knowledge of this true but unknown point. So if I were to sample using a Monte Carlo technique a whole bunch of initial conditions, and if I were to draw them, let's say uniformly from this circle C, if this were really the PDF associated with this true state, the idea I'm trying to sort of illustrate schematically here is that if we run a weather forecast model for 6 hours or perhaps 24 hours, the points that we would choose in the blue circle will over time get transformed into something that is roughly elliptical by the actual nonlinear dynamical system, which I'm just simply calling F here. So, a circle, a PDF that's originally a circle, gets distended into something that's an ellipse. But now if we think of this as all happening, let's say in a 3,000 dimensional space, and I'm taking maybe a couple hundred points here and following them under the evolution of some global weather model, what I'm saying is that in this notion of local low dimensionality, that for the most part, these points in this 3,000 dimensional space tend to get spread out in an ellipse whose major axis is roughly 40 dimensional. Okay, so of course it's this expanding subspace that is causing the error to grow. Okay, it's this error that eventually swamps our calculation, but this error, the growing direction of the error, is in a relatively low dimensional subspace. So if DJ's calculations are right, then typically this is something like 40 for a medium resolution model. The remaining 2,960 directions are here, And so the uncertainty in those directions, relatively speaking, is shrinking. Okay, so when we try to do data assimilation to reduce our uncertainty, if what we want to try to do here is to exploit the chaotic dynamics here, so as to try to reduce the uncertainty just in this expanding direction. So if we do this just in the expanding direction, then we really only have, if you will, 40 dimensions to worry about. And so by what we're going to do here in a rather elaborate mathematical technique, to try to change coordinates to this empirically determined subspace and do our Kalman filter calculations entirely in this subspace. And so by doing that, all the relevant matrices, instead of being, let's say, 3,000 by 3,000 or even larger, they're really 40 by 40, because we're not going to do anything to the analysis that's in this perpendicular contracting state. We're only going to make changes to the components that lie in this empirically determined direction of expanding error growth. Now, these directions that I'm talking about will differ from point to point across the globe. So the error vector over the direction of error growth over, let's say, France in this abstract space might be different than the error growth in a synoptic region that would be centered around Bangalore at a given time. But more or less, all these dimensions here will be, much smaller than the dimension of the total model state vector. And so that's the key dynamical ingredient, the key mathematical ingredient that makes this local ensemble Kalman transform filter very computationally efficient. Our application that I will talk about today, and the one that is reported in that TELUS paper from 2008, is to the global forecast system, which is the U.S. Weather Service model. The principal dynamical variables in that model are the natural logarithm of the surface pressure. Essentially, pressure becomes the vertical coordinate, virtual temperature, that is the temperature at zero humidity, and then the divergence and vorticity of the wind field. So these are the primary dynamical variables, but there are other tracers that get carried along, in particular ozone and water vapor. The measurements, the types of measurements that we will try to assimilate are the standard sorts of ones: barometric pressure, temperature, humidity, wind speed, and direction. In the modern era, of course, we have satellite radiance observations. This is actually quite a complicated subject. It's really a subject for another talk. But let me just say that with some assistance from our colleague Jose Aravecchia, who is with the Brazilian Weather Service, we have been able to implement this filter with satellite radiance data. That paper has just come out in Monthly Weather Review. I think it appeared about 2 weeks ago. So if you look for us there, you'll find the paper. Now, let me just start here with a slide of things that I think everybody knows. Certainly you've been talking about these types of ideas throughout the workshop, but just to fix ideas in notation, let me just run through this very quickly. So what we imagine here is that at a given time we have a vector of observations, let's say there's P of them, that we want to use to update our estimated initial condition for a complicated model. And those observations, we will assume, are some function of the true state of the atmosphere. So T here always stands for truth. So there's some observing function that if we knew the truth and if there were no error, we would we would have sort of perfect observations, but of course all the observations have noise, and so we assume then that these observations are functions of the truth plus noise, which in the simplest case we think of as Gaussian with mean 0 and some covariance matrix here that's called R. So wherever you see R, that's my notation here for the covariance of the observations. Now in the simplest case we can think of observations as being, to a pretty good approximation, as uncorrelated. For example, the errors in the airport thermometer at Bangalore are independent of the errors in the thermometer at the Rome airport, and so on. Anyway, so now we're going to take a model forecast that in meteorological parlance is often called the background or the first guess field. But our forecast now is a vector x with, let's say, n elements to it. Our actual forecast, the one we're going to work with, the background forecast, we will assume is the truth plus some error. Now that's probably not quite, well, this is a little bit of an oversimplification, but again we will suppose that this error is Gaussian. I'll talk briefly at the end about some issues with that, but there's not going to be time this morning to go into this whole thing in great detail. So let me just talk about the simplest case where, as with the observation errors, we'll suppose that the model is unbiased and that there is some covariance matrix associated with the background errors, which we will call P sub B. So B always stands for background, that's the model forecast. And so the usual Kalman filter approach here then is to try to minimize what's often called an objective function, but in any case it's a weighted sum of squares. So if the true state of the atmosphere were really x, our observations would be h of x. They would differ from the actual observations by this amount, and they would differ, and it would differ from the background by this amount. Now, one intuitive way to think about this is if you don't have a lot of confidence in your model, if we think of PB as being something that's relatively large, but we do have a lot of confidence in our observations, that is, R is a matrix whose entries are small, then when I invert R, the inverse of a small matrix is something that's big, and the inverse of a big matrix is something that's small. And so what would happen here is that we would tend to give more weight to the observations than we would to the forecast in such a situation. Okay, and so when we do this minimization process, and it is possible to write down a formula in the case of assuming a linear model and Gaussian errors and so on, it is possible to write down a formula for the value of x that minimizes a subjective function. We're not interested in those details, except just to point out that it is possible to do that. And so when you find the minimizer for the subjective function, then that is often called an analysis. In other words, we have analyzed the situation, we've taken into account our previous forecast, we have updated that forecast with new information to come up with an updated set of initial conditions from which we will then run the forecast model again for some period of time. And so in an operational weather center, what happens is that we have typically a 6-hour forecast that gets corrected. We have a new initial condition that's run for the next 6-hour period, and so on. And so what we hope to do with this is then to update our estimate of the uncertainty associated with this analysis state, and that uncertainty is reflected in a covariance matrix P sub A. So one of the big challenges and ongoing areas of research in all of this is if we knew what PA is at time 0, what is the most accurate way to evolve this covariance under some very complicated weather model. So ensemble filters are one approach to this, but they're not necessarily the last word on things. So again, just to recap here, so we're going to suppose that our observation errors here are normally distributed. Same thing with the model errors. And so one of the things that you can show, and this was Kalman's great breakthrough, is that if you assume an underlying model, dynamical model that's linear, then you can show that this minimizer is unique, it's unbiased, and it has minimum variance among the class of all linear estimators. So this is, in a sense, the best that one can possibly do. It's optimal in the statistical sense. Now, weather models, of course, are definitely not linear, but what one hopes, particularly in the case of a global weather model, is that it is linear enough over a 6-hour period that by performing this, this minimization, we'll still get something that is useful, and there's long experience to suggest that that is the case. But on the other hand, from a mathematical perspective, there's no theorem, no guarantee that this would necessarily be optimal. Okay. Now, this is all well and good, but the problem that has stymied people for a long time when they think about how do we use Kalman filtering in the context of a big weather model, and that's the curse of dimensionality, if you will. If we have a very high resolution weather model, and in current operations at the National Centers for Environmental Prediction, that weather model has grid points at roughly every 25 kilometers across the entire globe, and there's something like either 64 or 91 vertical levels to the atmosphere, and so you end up here with billions of points in your state vector, billions of elements in your state vector, and so that means that this matrix, P sub B, is basically 3 billion by 3 billion. It's absolutely gigantic, and the computational problem is that there's no way that you can think about really trying to invert such a large matrix. Now, the problem with handling the observations for the most part is not so terrible. The number of observations that are typically assimilated every 6 hours is much, much less than the size of the state vector. About 3 orders of magnitude less. But on the other hand, if you think of that this observation matrix is pretty much diagonal, then inverting R inverse is not necessarily so awful. So the whole problem here is what you do with the forecast covariance. Okay, so a naive implementation of the Kalman filter is simply intractable. And the reason it's intractable is that if you've ever taken a course in numerical analysis and you count how many operations does it take on a computer to invert a k by k matrix, you find that this is roughly an order k cubed algorithm. So if you look at a matrix that it has twice as many rows and columns, then the inversion time goes up by roughly a factor of 8. So if you can invert a 100 by 100 matrix on your Xeon computer, let's say, on order of 1 second, then trying to invert a matrix that's a billion by a billion would take somewhere on the order of 10 to the 18th seconds. Now, to get some idea how long that is, well, 1 year is roughly 10 to the 7 or 10 to the 8 seconds, and so here you're talking about something like perhaps close to 100 billion years. This is several times the age of the current universe. All right, so unless one invents a radically different computer or a radically different algorithm, this is just a hopeless problem. The other thing is, of course, that P sub B is not diagonal, and in addition, it's going to change with time in general. I mean, if you have a tropical cyclone approaching the east coast of India, let's say, the forecast uncertainty is rather different than on a day where the weather is fairly quiet. Now, so there are various strategies that people have attempted to undertake here to reduce the amount of computation. One is this notion of localization. That is to say, can we just try to do this minimization over some smaller region of the globe? So instead of doing the entire globe, maybe I will try to do try to minimize this Kalman filter, or try to do this minimization procedure and apply the Kalman filter over, let's say, India, and then do it over Russia, and then, or Eastern Russia, and then over France, and so on. That notion goes by various terms, one of which is called optimal interpolation. You simply chop off your model into some region of interest and do that minimization. The other approach, and this is what is done currently in operations, is to somehow estimate what this typical forecast covariance matrix might be and pre-compute some approximation of it. And what happens here is that this matrix is an object then that varies typically very slowly with time. There's typically a seasonal matrix, so the entries that would correspond to the forecast covariance over, let's say, North America would have one set of values in winter, another in spring, another in summer, and so on. Okay. The other type of thing that you can do is perhaps to combine this with some procedure for selecting a subset of the observations. You assimilate one observation at a time. You update the model state in some region around that observation, and so on, and then you have some criterion for discarding observations that you regard as redundant. Now, all these strategies have some important drawbacks. One is that, first of all, if you think of this forecast covariance matrix as being roughly constant, it tends to ignore what we call the errors of the day. That is to say that if you look at these, think about these spaghetti plots that we looked at yesterday, the forecast uncertainty tomorrow over, let's say, Saskatchewan might have a rather different structure than it does today. And so this is one thing that's often regarded as a roadblock, a stumbling block to getting better forecasts. So, of course, the weather models are definitely not perfect. They can certainly be improved, but this is definitely one area that really needs improvement. The problem when you assimilate observations sequentially is that your answer depends on the order in which you assimilate them, so there's a uniqueness problem here. And the difficulty with something like optimal interpolation, where you simply chop up your spatial domain into regions and do this Kalman by region filtering problem, is that you might get analyses that aren't necessarily continuous, and so continuity at the boundaries becomes a problem. So so we've all worked on this. This local ensemble transform Kalman filter, or LETKF as we call it, has built on work by a number of different people. Jeff Whitaker, Jeff Anderson at National Centers for Atmospheric Research in Boulder, Colorado. Craig Bishop, who's currently at the Naval Research Lab in California, Andrew Lorenk in Great Britain, and many others have looked at these notions of Kalman filters, and our approach is basically a refinement of some of these things, some of these ideas, to try to address these roadblocks here in terms of computational complexity in a way that we hope gives us nice continuous analyses. So our approach here is to exploit this notion of local low dimensionality. So we in an appropriate mathematical space, we want to do this Kalman filtering, and we want to do this in a space that is much smaller dimensional than the overall model state space. So that will make the matrices much smaller. Our procedure also assimilates all the data at once, so you don't have to worry about the order in which you will process the observations. The other thing that we will do is we will use localization in sort of the same spirit as optimal interpolation, but what we will do here is we will localize our assimilation of observations. So at a given grid point, what we think of is simply taking all the observations that lie within some radius of that grid point. Those would be the sets of observations that would inform our estimate of the current state of the weather. So, for example, if New York City were a grid point, we might take observations all around New England and the surrounding waters, but we probably would not take observations at San Francisco or Hong Kong because that doesn't tell us anything, at least in the next few hours, about the weather over in New York City. The other thing is that these computations are all done grid point by grid point in such a way that they can be run very efficiently on massively parallel computers. This is a non-trivial consideration because in any aspect of weather forecasting in particular, there are real-time constraints. We could have the best system in the world for estimating state vectors, but if it takes us 24 hours of compute time to figure out what the state vector is for tomorrow's weather, then it's not really very useful. And in fact, what the current operations center does in the United States is they allow about 20 minutes for the data assimilation step. So the whole thing's got to run in 20 minutes or less. Okay, so here are some of the ideas then that are employed in this local ensemble Kalman transform filter to try to reduce the computational complexity associated with the Kalman filter. So what we do here is we take an ensemble of size k. So there are k realizations, k different forecasts that of course form a set of background vectors. X here is the entire global state of the model. But now what I'm going to do here is to abuse the notation a little bit. And what I'm going to do is I'm just going to take a subset of this great big global vector and just work on a subset of the components in some particular region of interest. For example, if I wanted to analyze the grid point over New York City, let's say, I would take the elements of this global vector that would correspond to the dynamical variables of the GFS model over New York City and possibly some of its environs. So that would be a subset of a very big vector, and let's just call that L elements. And so what we would have here then is an L by K matrix that we're going to form. What I'll do here is take now the average of all of the components of this global background forecast vector that are relevant to, let's say, the weather over New York City. So I will find that mean that has size L, and then what I'll do is I will subtract that mean from each of the other relevant components of each of the different K forecasts for New York City, and that will give me what we call a background perturbation matrix. So each column of XB is the difference between the corresponding forecast and its mean. Okay, so the ith column is the appropriate elements of the global vector minus the mean for those components that are relevant, let's say, to the weather over New York City. Now what's going to happen, of course, is that I'm going to repeat this calculation, for New York City, for Montreal, for Toronto, and so on and so forth for every grid point in the weather model. But for the moment here, I'm simply going to describe what happens at a particular grid point. In this case, let's just imagine New York City. Now, what happens here is that because these weather models seem to exhibit local low dimensionality, then a relatively small ensemble provides a pretty good approximation of the PDF of the forecast uncertainty at a given grid point, let's say over New York City. So what I will do here, I don't know what the true forecast covariance is, but what I will do is estimate it by simply taking these perturbation vectors times their respective transpose, because remember the mean of these columns is 0 because I've subtracted off the mean. Okay, so this becomes a nice symmetric positive semi-definite matrix. Its dimension here is going to be, if you look at this, it's going to be let me see here, I think L by L, no, K by K. Anyway, so it's going to be but this will be a low rank approximation of the actual forecast covariance matrix at a given grid point. The other thing I will try to do is to localize the observations by drawing a circle, let's say around New York, and only use those observations that are relevant to the weather over, let's say, the next few hours, because I'm going to do this 4 times a day. But the whole idea of this LETKF formulation is to try to find a linear combination of the columns of the background perturbation matrix that best fits the observations. And what I mean by that, by best fitting the observations, is in the sense that it will minimize this weighted sum of squares in some appropriate subspace. Now, if you've been listening carefully here, and if the mathematician in you might say, wait a minute, there's a problem here, because this matrix of background perturbations, well, there's enough columns. There's one column for every ensemble solution, so there's k ensemble solutions. I've subtracted off the mean, and so what that implies is that if I sum up all the columns of XB, they have to add up to 0. Okay, and so this is a matrix here that cannot have full rank, and so in fact the rank of this estimating matrix here, P sub B, that I'm saying is my estimate for the background covariance matrix, its rank is at most k minus 1, and so there's a potential mathematical difficulty here in that I can't talk about the inverse of a matrix that's singular. Now, this idea, to the way in which we work around this, is really due to Brian Hunt. This is a very clever approach to circumventing this difficulty. And one of the ways in which you think about circumventing the difficulty is that the rank of these ensemble perturbations is almost certainly k minus 1. And so what we can do is think of this matrix itself as a linear transformation from some k-dimensional space to something that is 1 dimension less. Now, every matrix is going to be 1-to-1 on its column space. And so what I want to do here is try to perform this minimization here in this abstract k-dimensional space in such a way that it makes sense to think about inverses. And so the way we will do this, and this is the trick behind the local ensemble transform Kalman filter, and this is also what makes it very very computationally efficient, is that we're actually working in some k-dimensional, abstract k-dimensional space. Now, that abstraction can be made more concrete in the following sense. What I want to do, try to find an appropriate vector W that does that. Well, W is simply a linear combination of all of these columns of XB. Now, it doesn't matter necessarily in this case. It really doesn't matter that the columns all add up to 0, or that they're not all linearly independent. Instead, for every vector that I would choose, every linear combination of those that I would choose, I get a vector that now lies in some k minus, in some space here whose whose dimension is k minus 1. And I will now think of every model state as the mean plus this linear combination of background perturbation. So for every W, there really is a corresponding actual model state in model coordinates. So this is the relationship between some abstract mathematical space and something that the model itself understands. Now, the setup has the following property, that if W in this abstract space is a Gaussian random vector whose mean is 0 and whose covariance is this particular multiple of the identity, then you can show that this vector x in the model space also is Gaussian. Its mean is xb. This should be in bold, I'm sorry. So it's mean with the same mean, and its covariance is this empirically determined ensemble covariance matrix. So that is a very important and very useful property of this formulation. So we can go very readily from an abstract space to a model space in a way that if things in our abstract space are Gaussian, then things in our model space are Gaussian. And so if you do all of the algebra, and there's quite a bit of technical steps here, but this is all done in the Physica D paper, it turns out that you can rewrite in an equivalent way this sum of squares, this weighted sum of squares, in such a way that the background covariance matrix is in fact the identity. So this is the weight that we're going to give to the background forecast. And this term here on the right is the weight that we're giving to the observation. So plain old y here is actually our vector of observations, and these other terms here are our observation function, and I'll explain in a couple slides here how I get these other things. So point is, we can rewrite the Kalman filtering equation, or the objective function for the Kalman filter, in this sort of natural way. And it turns out you can also show that, is there a question? Sure.
So W is in k minus 1 dimensional space, right?
Right.
And XB is L cross K. Did you form some XB hat from XB?
Let's see here. So I think my previous slide, I think I could have stated this better. So S is a k minus 1 dimensional subspace of S tilde. Okay, so S tilde is a k-dimensional linear space. Okay, and S is a k minus 1 dimensional linear subspace of S tilde. So this is still a k vector.
Okay, yeah, fine. Thanks.
Yeah, it's a k vector, but it's sitting in a subspace that's one linear dimension less than the original one. Okay? Yeah, I should have been clearer about that. Okay, yes. So everything here is k-dimensional. It's just that the span of this is k minus 1 dimensional. Okay, so you can turn the crank and you can write down this weighted sum of squares and minimize it in such a way that once you have found a minimizer, okay, you can show that this minimizer is perpendicular to the null space of XB. That's very nice. And also you can show that by, remember, with every vector I choose in S hat, there's an actual model state. And in particular, what you can show is once I minimize this J tilde, then the corresponding model state minimizes the original sum of squares that I would have set up with the Kalman filter. And in fact, what happens here is this is precisely the way in which we update the mean, the ensemble mean, with the data. Okay, so what I'm going to try to do here, what I will do is use the data in such a way that I find a minimizer W sub A of this quantity. I will take a linear combination of the background perturbation vectors, add them to the original background mean, and that will become my new analysis mean. Now, what remains to be done, of course, if this is the analysis mean, I need to find, well, what are the actual, what's the analysis ensemble? Okay, so I know the mean of that ensemble, but of course there are many different ensembles that would have the same mean. Now, again, as sort of a global cartoon here, I might be doing this procedure that I just outlined on the previous slide over, let's say, New York City, and I would be taking observations that would lie in some region around New York City. Maybe this is roughly a 1,000 by 1,000 kilometer square, and so the vector y that appears in that previous slide are the components of the global observation vector that lie in this particular region over New York City. Now, I'll do the same thing over Toronto. Let's say if Toronto were a grid point, I would be drawing another box, so let's say 1,000 by 1,000 kilometers, and I would be repeating exactly the same calculation over Toronto using a slightly different set of observations. And in fact, what I would be doing is drawing a similar box around every other point, grid point, of my model. Now, one of the things that's important here is that if you have grid points that are relatively close together in space, for example, New York and Montreal, or perhaps Bangalore and Mumbai, they will have overlapping sets of observations, okay, if these boxes are big enough. And so as I go from grid point to grid point, the set of observations that I'm using is changing relatively slowly in space. So for example, the observations here that I would be using over New York City wouldn't be that much different from the observations that I might be using at Montreal. There would be a fairly large overlap. Of course, in Montreal, I would be taking observations that lie further north than the observations that I would be taking at New York City, but that's okay. So assuming that our observing network is sufficiently dense, the set of observations that we are assimilating at every grid point is something that's varying relatively slowly in space. And that's important because what it means, we've set things up so that if the set of observations varies more or less continuously with space, then our analysis, our choice of W's here will also change in a continuous fashion. And so that means that we won't get a radically different analysis over Albany than over New York, provided that our set of observations lies over a sufficiently large geographical area. Okay, so how do we treat the observations in this format? Well, for each ensemble realization, I have an observing operator, and so there are, of course, k ensemble solutions here. Each solution would predict a slightly different observation at each observing location. But what I will do is I will calculate this observation operator for every one of my ensemble solutions, and I'll take the mean of that vector, or at least the components that are sitting in one of these colored squares, one of the regions in which I agree to assimilate observations. So let's suppose that there are S of these observations. Then what I'm assuming here, of course, is that the perturbations about the original ensemble mean, the background ensemble mean, are not so enormous, so that I can approximate H, I can linearize H about the ensemble mean of the mean of H applied to all of the ensemble vectors. I can write that as a linear combination of observation perturbations. That is to say that this vector y is constructed in the same spirit as the matrix capital X. Each of its columns is the predicted observation for that given ensemble solution minus the mean of over all the ensembles. So this is, if you will, an observation perturbation matrix. And what I'm supposing is that by taking linear combinations of that perturbation matrix and adding them to the mean vector, I can get something that pretty well approximates the actual observing function. Now, if your observing function is simple linear interpolation, for example, you've got the temperature halfway between New York and Albany, and so you average the temperatures between New York and Albany and you call that H, then this is now an exact equality. But there are cases here where H might be something nonlinear, particularly in the case of, let's say, some sort of satellite radiance observation where maybe H is a fairly complicated function, some sort of radiative transfer function. Okay, but again, we're only going to use the components here that lie within one of these boxes here. Let's see, oops. That lie within one of these boxes around the particular grid point that we're analyzing. So for New York, I might go perhaps 600 kilometers east and west, and north and south, and likewise over Toronto and so on. So I will only pick the elements of the observation vector that lie within, let's say, this blue square. Okay, and so then it turns out, again with a fair bit of algebra that I won't have time to discuss, and besides I'd put you all to sleep if I haven't already, but let me just kind of give you the sort of the overall net result. And it turns out that you can calculate something that is the equivalent of the Kalman gain matrix in this formulation. And so the term here in parentheses is our innovations, right? This and what we have here on the left is a collection of matrices that's going to tell us how we apportion the discrepancies between the actual observation and, let's say, the mean predicted observation to give us a linear combination or a vector in our original space that's going to tell us how to take linear combinations of our background perturbation matrix in a way that minimizes the original objective function sum of squares. And it turns out that this matrix Q here is the identity plus something, a weighted thing here that involves the observation covariance and the observation perturbation matrices. So once I've calculated this vector WA, I then use it to update the background mean to give me the new analysis mean. What remains to be done is to calculate the rest of the analysis ensemble. That is to say, I want an ensemble whose mean is X sub A, and that has basically the right statistics. And it turns out the way that you do that is by calculating now a K by K matrix, capital W, and that will tell me the linear combination that I should take of all of the background perturbations to come up with XA, which will now be the analysis perturbation. So to get the analysis ensemble over New York City, what I would do is add the analysis mean to each column of this particular matrix. And that would give me my updated model state over New York. Now again, in parallel, all of this stuff is being calculated for every other grid point simultaneously. And so this set of updated grid points obtained in this manner becomes my new global analysis state vector. Now, there's one point here, and again, this is more of a technical detail, but us that WA is a symmetric square root of this matrix Q. This matrix Q here is clearly symmetric because by virtue of this term. Remember, R is a symmetric covariance matrix of the observations. Here's the identity matrix. And by taking a symmetric square root, you can show that this WA depends continuously on the elements of Q. That's very important. And also, by taking this choice of a symmetric square root, we can show that the columns of XA sum to 0, which would give us the correct sample mean for the analysis ensemble. Now let me say a few more words about this, and then the rest of the gory details are in the Hunt paper in Physica D. Unlike, let's say, a real number, a matrix does not necessarily have a unique square root. So if you start off with a symmetric positive definite matrix, one way to define a square root of that is to say, well, if I have a matrix S such that SS transpose equals A, then that I will call that the square root, or a square root of A. Now, for those of you who have done numerical analysis, you'll recognize this as a Cholesky decomposition in the case that A is symmetric positive definite. On the other hand, as far as square roots go, this is not necessarily unique, because if you take any other orthonormal matrix, then S times U is also a square root of A, because if I take that matrix times its transpose, I will get A. Okay, so S is unique up to a choice of orthonormal matrix. The other difficulty with a Cholesky decomposition is that it is not necessarily continuous as a function of the elements of A. I can change an element of A a little bit and end up with actually a rather different factorization. So that's not very good for our purposes, because we don't want the linear combinations that we're taking of our background perturbation matrices to vary radically between adjoining grid points. So instead, what we want to do is to take a symmetric square root, which we can calculate in the following way. Again, we're starting off with our matrix A, and so let's calculate its eigenvalue-eigenvector decomposition. And so if D is a diagonal matrix of eigenvalues, and V is the corresponding matrix of eigenvectors, and let's choose those eigenvectors so that they're normal, they will certainly all be orthogonal to each other if A is symmetric. And so I have this relationship. And so our choice of square root matrix is simply to take the square root of all of the diagonal elements here, square root of the eigenvalues of A. Because remember, if A is a positive definite symmetric matrix, all these elements here will be real, and so there's no problem taking the square root of each of the individual elements. And so, as I said, this is enough to show that the columns of our analysis perturbation matrix will sum to 0, which gives us the right sample mean, and it's also, you can also show that this choice of S will depend continuously on Q. And again, the technical details here are in this paper. Another thing that is useful to think about here is the computational complexity of this scheme. If you actually had to program this up and put it on a computer, how much work is it? Well, you know, the nice thing about this local ensemble transform Kalman filter is that in principle, the only free parameters that you have are the ensemble size K and how big a local region you want to take around each grid point from which you will select observations. So if that local region has S observations and your ensemble has size K, then it turns out that the most expensive step by far is calculating this quantity that is used to generate essentially the analysis covariance matrix. The second most expensive step is calculating the symmetric square root, and then you also have to look up observations, but that's quite inexpensive. So really, once you fix the size of your ensemble, all your calculation, your most expensive calculational step is basically linear in the number of observations. So that's that's really a very nice property. Now, the thing is that, we calculate this grid point by grid point, but all the grid points are updated independently of one another. And so in a given parallel implementation, it turns out that you can use something like MPI to distribute all the data across a big cluster only once. And I've written a load balancing algorithm here that actually the Brazilians tell me it now scales up to 256 processors, because the Brazilian Weather Service is actually using this formulation, this local ensemble transform Kalman filter, as the basis for their next generation data assimilation system. And so you can take a fairly large model. This is a model with where grid points are roughly 150 to 200 kilometers apart. I can assimilate 250,000 observations in 3 minutes on 16 relatively old Xeon processors. So remember, the operational. In an operational center, they allow 20 minutes for their current scheme, so this seems like it will work very well in an operational system. In fact, the greatest expense in putting all of this together into a real analysis system is actually in running the model to compute the forecasts. But that's also embarrassingly parallel. You can simply send off one forecast per computer for each ensemble that you want to follow. All right, so some key properties here. This is really the take-home message, is that this is a formulation here that calculates not only an analysis, but also an estimate of its uncertainty. That's important. It assimilates all the data at once. This observing function can be a nonlinear one of the state vector. It turns out that you can extend this entire formulation to deal with observations that are not necessarily contemporaneous with the analysis time. So in what I've told you, I've made the simplifying assumption that all your vector of observations all becomes available exactly at the analysis time, but one can extend this to take care of observations that are taken in between the 6-hour period at which you're updating your weather model. And as I said, the only free parameters in principle are the ensemble size and the size of the local regions. One of the potential advantages of this formulation is that nothing that I've told you depends in any way on the details of the equation of the actual weather model that you're looking at. In something like 4D VAR, you have to integrate an adjoint equation, and so in a 4D VAR setup, if you change your forecast model, then you have to change your data assimilation system, and this adjoint requires that you linearize the model, and that's a pretty time-consuming and difficult thing to do for a big weather model. So with a relatively small research group, we've actually been able to implement this LETKF on a number of different systems. Besides the global forecast system for the U.S. Weather Service model, we've looked at a model of the Martian atmosphere. We've looked at several different ocean models. And we've even actually, we're experimenting with this for a model of cancer growth and thinking about whether one can forecast cancer using some of the same technology that's used to forecast the weather. Unfortunately, I don't have time to talk to you about that. That's another talk, but maybe at a future workshop, if we get some results, I can tell you about that. In any case, let me summarize briefly what happens here when we actually try to use this LETKF with a global forecast system model. Now, because our computers at the time weren't so powerful, we were running the global forecast system model at T62 resolution. This was the resolution that was operational up until the early 1990s, so it's a well-tested resolution. The operational forecasts over in 2004 were done at a much higher resolution, grid points roughly every 50 kilometers, as opposed to roughly every 200 kilometers. But we're going to take those operational analysis as our surrogate for the truth, because we don't really know the true state of the atmosphere, but we will suppose that the operational analyses for the high resolution model are the truth. And what we've done is we've run our data assimilation system on all the data that would be used operationally except for satellite radiances. And we used an ensemble, in this case of size 60, but the results don't change very much whether we use 40 or 80. 60 is a little better, but not enormously so. And what we've done is to try to track the weather over the winter season, more or less, January 1st to March 1st of 2004. And what we're doing is we're going to compare our system with the operational system run on this same data and with a forecast model run at T62 resolution. And I'd like to thank Zoltan Toth and his co-workers at NCEP for making these data available. So one of the ways in which we can try to assess how well we do is to look at a root mean square difference between, let's say, a forecast, say at 48 hours, and its difference from the truth, which in this case is the high resolution analysis. And what we can do here is to compare that with our system versus the NCEP system by doing this RMS average over all 48-hour forecasts run over roughly a 6-week period. And on this figure here, we have some sort of representative results. This particular column here is for the southern hemisphere. The right-hand column is for the northern hemisphere. And the rows are for temperature, for geopotential height, and for one of the components of the wind. For the temperature here in the southern hemisphere, we are looking at forecast error or RMS error in Kelvin. And the lower scale here, in case you can't see it very well, there's 0, 2, 4, and 6 degrees Kelvin. And the vertical scale here is in pressure. 1,000 hectopascal is more or less the surface of the Earth running up to the top of the model atmosphere. There are two curves, a left curve and a right curve. The right curve corresponds to greater forecast error. The left curve corresponds to smaller forecast error. And the left curve here is, in fact, how the local ensemble Kalman transform filter does over the southern hemisphere. So our forecast errors for temperature are much less than for the current operational system, at least for these data and for this model resolution. Over the northern hemisphere, the differences are much less. And the reason is that the northern hemisphere is much more densely observed than the southern hemisphere. So it seems that this procedure, this local ensemble Kalman transform filter, is particularly efficient when you've got sparser sets of observations. And this discrepancy in forecast error holds up. There are qualitatively similar results here for geopotential height and for the wind. And also, our errors are much smaller in the upper stratosphere here. Again, a part of the atmosphere that isn't particularly well observed. And so, on the strength of these types of results, the Brazilian Weather Service was very interested in our scheme because, of course, Brazil is in the southern hemisphere where there isn't as much data available. Here's a picture that shows, again in this RMS sense, where we tend to improve our forecasts in a spatial domain compared to the current standard practice. So negative numbers here means improvement, and positive numbers mean where we have some degradation in forecast accuracy. So we have where we have our greatest improvement in forecast accuracy here is to the southwest of the southern tip of South America, and this actually is a region that turns out to be one of the most sparsely observed regions on the entire globe. But we do pretty well off the southeast coast of the United States and also over much of Africa and the Indian Ocean. And again, this is an area where observations tend to be relatively sparse compared to land. There's a few places where we are mildly worse, somewhere off the west coast of Central America and so on, but we're not awful. Our improvements, let's say, tend to be much better than our forecast degradations. So I think my time is about up, but let me just close by saying that not all problems are solved, okay? There's still plenty to be done here. One of the many problems that we face in modeling of both biological and natural phenomena is that no model is perfect. And what happens here if we relax this assumption that our model error is both Gaussian and unbiased? Okay, everything that we've done here is optimal only in the case where we assume a Gaussian unbiased error, and we know that that's not the truth. There are cases where the available observations here are really only very loosely coupled with the actual dynamics, and another other very important error is the error of what we call representativeness. In a global weather model, a lot can happen between grid points. A thunderstorm, an individual thunderstorm cell is on the order of 1 kilometer in radius, but if your weather model only has grid points every 10 or 25 or 50 kilometers, then the question of how you represent convection becomes important, and the measurements that you're taking are actually being affected by conditions that or by dynamics that are happening at scales that are smaller than your model can resolve. The other problem here, and this is an intrinsic one with ensemble filters, is that because the model is nonlinear, it turns out to be the case that your ensemble covariance matrix tends to underestimate the true uncertainty after a period of time, and there has to be some sort of variance inflation, if you will, to keep the filter from diverging. So that's the art, or that's where art meets science at this current point, but there's a lot of research going on this question. So in conclusion here, we have a system here that I think is at least worthy of serious consideration for research purposes and possibly also for operations. We seem to have a filter here that works very well where observations are sparse. This seems to work very well for atmospheric data assimilation, but it also works for the ocean too. We're working on that. The fact that it's independent of the model equations makes it very readily adaptable to different situations, and it's a pretty well-tested ensemble-based Kalman filter. In conclusion, I'd like to thank lots of folks who have funded us over the years. I've received funding from the National Science Foundation, from the ASU College of Liberal Arts and Sciences. Much of the Maryland group was initially funded by grants from the Keck and McDonald Foundations. We're also grateful to funding from NASA, where we started looking at the satellite radiance problem. The Army Research Office funded early versions of this work, and the National Centers for Environmental Research, or Environmental Prediction, were very generous in making data available to us. Thanks a lot, folks. It's been great. If there are any questions, I'm happy to take them.
Any questions for Eric? Actually, you probably need to run your meeting.
Okay. Can you tell us a little more about
Okay.
Yes, I can hear.
more about ingesting satellite radiances directly using LETKF? A little more about what's been done.
I can summarize briefly. As I said, we have a paper that's come out, I think, in the most recent issue of Monthly Weather Review. But there are two problems with processing satellite radiances. One is that the radiative transfer model there really are problems here with model biases, and you need a way to try to estimate those model biases. It turns out that you can actually use the LETKF to try to estimate what those bias parameters are if you assume that those bias parameters are approximately constant in time. The other type of problem that arises with satellite radiances is that, as you probably know, there's a weighting function that's associated with it. So there will always be some vertical layer in the atmosphere where the instrument is, let's say, particularly sensitive, and so you have to figure out when you're doing this localization vertically as well as horizontally, at which grid points do you assimilate that particular radiance.
Other questions?
See, when you mentioned this sequential observations, you also mentioned the uniqueness issue.
Right.
I didn't fully understand. So what is the uniqueness issue? The second question is that in your method, you have avoided sequential observations. Do you have a uniqueness issue in your method?
Okay, so let me see if I can go back here. There's a couple of questions, and I think where this uniqueness issue comes in is, first of all, when we want to calculate this weight matrix that is coming from a square root of this particular object, which is essentially going to be our analysis covariance, as it turns out. Okay, so there's not a unique way to think about, there's not a unique matrix square root, but we're trying to pick one in such a way that we get the appropriate sample mean. Now you can also show, as far as uniqueness goes, that when you minimize this particular sum of squares, that this minimizer that you find is unique and is perpendicular to the null space of your background perturbation matrix. So with those two things in place, there's no ambiguity in how you choose your analysis ensemble for a given set of observations. Does that answer your first question? Okay, now remind me again on the second question is, how do we select the observations?
No, sequential observations.
Sequential observations, okay. Well, the problem if you want to assimilate observations sequentially, if I take observation number 1 and now I'm going to update my state vector using that information, and then I take observation number 2 and update some other components of my global state vector and so on. The result that I get depends upon which observation I assimilate first and which one I assimilate second and so on. So it depends very much on the ordering. In this particular formulation here, we're taking the entire vector of available observations and putting it into the analysis. So the order in which these appear as elements is really immaterial, as long as as long as we're consistent in our ordering, as long as that order is consistent with the error covariance of that given observation.
Yeah. Thank Okay, hang on a sec. Do you want to come up here so he can hear? I don't know if one of the students has a question, so
Sure.
come up here and then.
Maybe I have not followed the concept of localization fully, but according to my understanding, when you do the localization and in a small region, then when you calculate your background error covariance matrix, so you won't be having problem with the remote correlation, but you might lose some important information because your size of your covariance matrix is small. So,
Well, that's all. It's always possible that you lose something here. Let's see if I can find my picture real quick. So where the localization comes in, what I mean by a local region here, the localization simply affects the choice of observations that I want to assimilate to update a particular grid point. So if this were New York City, my localization radius might be such that I'm taking into account only observations over New England and surrounding waters, for example. The analysis, this whole matrix formulation that I've described, is simply for the components of the global state vector that are relevant for New York City.
I have one more question. So when you have selecting the ensemble members, so you have selected that you told that 40 members can explain the mean and variance properly.
Right.
So how do you make sure that these ensembles, these errors grows? So you also mentioned about the inflation. So
Right.
So how do you decide about that?
Okay. Well, a couple comments. I think these are very good questions. The way we actually generate the ensemble is we let this whole scheme spin up. And so what we do to start with is we take analyses for over the entire winter period. So we take the analysis for, February 25th and March 30th and December 30th and so on. And that becomes our starting set of initial conditions. So they are very uncorrelated with one another. But once we spin this up, and it spins up within a couple of days, then we actually have a forecast ensemble that rather quickly begins to track the truth. This problem of variance inflation is actually an important one, and it can be handled here by multiplying by a particular constant. The reason you tend to underestimate the background uncertainty after a while is because your model has nonlinearities in it, and so even if you started off with an ensemble state that was, let's say, Gaussian, by the time you run a forecast on it, it's not exactly Gaussian anymore. And so but all the arithmetic that we've put into this assumes Gaussianity everywhere. So the problem of how you pick these inflation factors is actually a very important one, because if you don't inflate your ensemble, after a while the filter will diverge from the truth. And what I mean by that is if the ensemble collapses, what you're saying is that your estimated background covariance is essentially going to zero, and that means you aren't giving any weight to the observations after a while. You tend to have to inflate more where you have densely observed regions. Assimilating a lot of observations into a given local region is something that tends to compress the ensemble, and so we end up multiplying by a number that's rather empirically chosen. It's been picked by sort of tuning things a little bit, but it's typically a number that's anywhere between, let's say, 10 and 25%. So what happens here is you simply take the background perturbation matrix and multiply it by a number that's about like 1.1, let's say. This is a bit of a wart on the whole scheme. It is something that is rather empirical, but it's also a problem that affects every ensemble method. And I would say from a mathematical perspective, all the exact reasons why these ensembles tend to collapse and so on isn't terribly well understood. And so that remains an area of active investigation.
Thanks. Is there anything else? Any other questions? So I have one question, Eric, which is sort of related to this. Does the pre-specified region is the same at each grid point? I mean, in the southern hemisphere where you have sparser observations, do you have a larger localized region?
Yes, generally we do. It's both good and bad. I mean, the observations that you're assimilating, have to be dynamically correlated with the grid point that you're trying to analyze. We've had some difficulties, let's say, on the coast of Antarctica, where there might only be one observation in a 1,000 kilometer region, and it happens to be an observation that sits at the base of a very tall ice shelf. And so what happens is, if that's the only observation that's available, then you'll update that grid point. Let's say here's one point on the coast off the coast of Antarctica. Then at the next point, there's no data at all, and so there can be some discontinuities in your analysis vectors here. That can be bad, because then it can excite gravity waves or other types of spurious dynamical behavior, because perhaps your analysis isn't the atmospheric balance might not be particularly well respected by your given analysis. So this does rely on observations being, let's say, generally readily available. But in the satellite era, that's pretty true. There aren't large areas of the globe anymore that are large data voids.
Okay, thanks. Do you want to know something? Okay, let's thank Eric again very much for staying up and talking with us.
My pleasure.
Okay, well, thank you.
Thank you for having me.
Yeah, I presume you'll be in email contact if the students have questions as they're doing their projects.
Of course, yes. I'd be happy to answer questions and direct you to papers. I can send you a PDF if you want one.
Okay, great. Thank you. Okay.
All right, thanks very much.